So Professor Eldho is currently Institute Chair Professor and Head Department of Civil Engineering, Indian Institute of Technology, Bombay. He obtained his PhD in Civil Engineering from IIT Bombay. Thereafter, he was postdoctoral fellow at the Institute for Hydromechanics, Institute of Karlsruhe, Germany. From Eldho, Professor Eldho's research interest is on water resources and environmental engineering. He has a long list of awards and accolades to his credit. To mention a few, eminent water resources scientists instituted by Indian Water Resources Society of India, Jal Vigyan Puraskar by Indian Society for Hydraulics, DARD Research Fellowship by the Government of Germany, Certificate of Merit Award by the Institute of Civil Engineers, and many more. He serves as the editor and advisory board member of several journals and different publishing houses of international repute. So before Professor Eldho starts, a couple of instructions for our audiences. We request the audiences to post their questions into the Q&A tab for Professor Eldho at the end of the talk. Please do not post questions into the chat box, and in case of any internet issue, please stay with us. Now, I would like to invite Professor Eldho to deliver his talk. Over to Professor Eldho, please.
Okay, thank you, Srija, for giving an opportunity to share my experience and whatever my research work in the area of groundwater pollution, remediation, and management. I'm very happy to see that American Chemical Society of India is organizing this kind of events for entire research community in the country. And now, though I am not a chemical engineer, but I work in the area of environmental engineering, and of course, pollution is one area which I work. And then today we are going to discuss. So since I understand many of you may be chemical engineers or chemists. So with respect to this, some interesting aspect is that since the main connection is that everybody use water. So I say how our water source or the water we drink can be polluted, and then as engineers, as chemical engineers or chemistry or bio engineers, what we can do to develop innovative techniques as far as the remediation, groundwater pollution issues, remediation and management. So this is what we are going to discuss in today's lecture. So I'll be having around 40 minutes lecture, and then around 20 minutes we can have a discussion. So my presentation outline include so many of you may not be from the groundwater area, so I will have a brief introduction about groundwater, and then we will discuss about groundwater pollution problems. So why groundwater is so important, and then what are the sources of pollution, why it is polluted, how it is polluted, and then as a common man or common person, how you can protect your groundwater. So since most of you, I am sure that other than cities throughout the country, everybody will be having their own wells, and then they will be using directly the groundwater. So how we can protect the groundwater and control the pollution. And then say, of course, you see that many parts of the country, and then many countries, say like especially Europe, Germany or America or other countries, groundwater pollution is a major issue since so much of industrialization took place in say after 1950s, and then this has led to a lot of pollution problems, especially water pollution, and that is especially groundwater pollution. So we'll be discussing how to do, what are the remediation techniques available, and as scientists and engineers, what kind of technologies we can look into. And then of course, since as a civil engineer, I am a modeler also. So groundwater modeling, how we can do modeling, some mathematics, how we can done. And then I will be presenting few case studies, how if an area is polluted, how much money to be spent, how much time is to be spent. This model, these case studies will show how the situation and what kind of things we can do. So that is what we are going to discuss today. So I am sure that all of you know what is a hydrological cycle. So you see that water is contained there. So whatever the water available on the earth, it will be going as say it will be evaporated, and then it will be coming back as a precipitation, and this is a cycle. So we can see that this groundwater is also part of this hydrological cycle. So here you can see in this figure what is happening. So here you see that once the water is evaporated, it will be, say, again going further in a cyclic mode as a condensation, and then it will be coming as precipitation, and then it will be, some water will be penetrating down, percolating down, and then we call it the aquifer system. That is what is so-called groundwater, and that will be going down and it will be stored. So we say, call it as the groundwater as a water bank. So like we deposit money in the bank, whenever we need, we can take it. So similarly, we can store a lot of water in the ground and subsurface. So there, and then that water is also moving, and then we can take it back through wells or as a bore wells, all those things. And then some part of the water will be going as a runoff, and that will be coming as surface water, and then this water again joining back to the sea, and then that cycle will be repeated. So this is in hydrology we call it as a hydraulic cycle, and this groundwater is an important component of the hydrologic cycle. So that is what you can see in this slide. So now, why groundwater is so important? So I'm sure that many of you are be using the groundwater, but you do not know it is very important source. So you see that we look at the water availability. So also all of you know that fresh water is hardly 3%, and then remaining 97% is say saline or other kind of water, so which we cannot utilize. And then out of the fresh water available, so almost 68% is in ice cap and glaciers, and then 30% is in the groundwater, and then surface water is only hardly 0.9 water, and then available water out of that, again if you come into this thing, so here so that way if you put into, almost 99% of the water is unusable, and only 1% of the water is usable. And out of that, that is the importance of groundwater, out of that 1%, even 99% of the water is groundwater, and only hardly 1% is there what we can observe really in the lakes, rivers, like that surface water bodies. So that is the importance of groundwater. So groundwater is a very important water source. And then many of the plants also get water. Most of the plants get water through groundwater source only. So that way we can see that this groundwater is so important. So now, as I mentioned, in till 1970s and 1980s, everybody thought that groundwater is a very pure source of water, and then so nobody bothered much about groundwater. So that way, now if you look into this, what are the problems as far as groundwater is concerned, and groundwater pollution it can pollute. So now if you can look into groundwater, what are the important problems? So you can see that there is so much of the problems are there. So one important problem is quantity is concerned, groundwater overdraft. You see that those are in India. You could heard about the so much groundwater is drawn in Punjab, Delhi region, and then it is going drastically down. So farmers are putting their wells with 900 feet or 100 feet down, and then trying to extract water. So that is a major issue in many areas. But some area water logging is a problem. So you see that water logging means already the surface, already too much water is there, and then we cannot use that area for even for farming. And then coastal region, there is a seawater intrusion problem is there. So that is another problem. And then that is about the general issues are concerned. Now coming back to, so much groundwater is available, but if it is not good quality, then it is useless. So that is groundwater pollution is a major problem. So we need to see within this context, we have to preserve the groundwater. So it is so important. So I hope those who are hearing me, all you understood what is the importance of groundwater, why we need to protect the groundwater, and what are the pollution problems. So groundwater quality is much decreased due to rapid industrialization and human mismanagement. We have to say this mismanagement, since we are controlling the many things, and then if we are not doing things many places, like if you go to Patanjali in near Hyderabad, or if you go to Palar in Tamil Nadu, many locations we can see that so much of industries, they did not treat the effluent properly, and then they simply deposited this their effluent in either underground or in the surface water itself, and these are all causing the big pollution. So that way, when we look into, let us see what are the contamination sources as far as groundwater is concerned, what are the contaminant sources. So here, this figure shows what are the important sources of contamination. So you can see that it can be we ourselves, like whenever we are putting our human excrete, all those things, septic tank, if there is a leakage, then that can pollute the groundwater. And then also say if you are dumping anything on the surface, so nowadays monsoon is ending, so this whatever is we are putting, that will be going to the surface water and then groundwater. And then farmers are concerned, they use a lot of pesticides and fertilizers. So this you can see that slowly penetrating down through the soil, and that is so-called distributed or non-point source of pollution. And then if many industries use their underground tanks, especially in petroleum products in India, still we are using underground tanks. So these tanks may be having many places a lot of leakage, and that can pollute the groundwater system. And then you see that many locations landfills are there. We use it as if you ask any environmental engineer, then the landfill is a major source of like we dispose the waste through landfills. So that we can see that leachate will be produced, and that will be slowly circulating down to the aquifer system or the groundwater system. So that way we can have, and natural contamination means you see that arsenic, you can see in Bengal belt there is a arsenic problem, so much groundwater is extracted that region, it is naturally happening, and then also seawater intrusion, so that is natural way of contamination. So important contaminant sources are natural contamination, agriculture contamination, industrial contamination, underground storage tanks, land application and mining, septic tanks, waste disposal injection wells, landfills, etc. So these are some of the important sources of contamination, as you can see here. So now, if you look into, so as I mentioned, when groundwater is concerned, we need to see that not only quantity, too much quantity is there, quality is not good, it is not at all usable. So quantity and quality are so important. So it is useful only if quality is safe. So that is very important. And quality indicator generally, since many of you are chemical engineers or chemists, so you can see that quality indicated generally by dissolved suspended solids. So that way, depending upon the pollution sources. So here again, I have listed number of pollution sources. So it can be, this pollution can be in the form of dissolved salt, domestic or industrial waste, heat, radioactive material, pesticides, manures, etc. So these are the way the pollution takes place. And then we look into this pollution, how it is going through the water. There is different ways the process are there. One is diffusion, of course, diffusion, then advection or convection, and then hydrodynamic dispersion. So this is important processes that will be taking place once this contamination goes to the groundwater. Then it will be slowly spreading like this. So that is what you can see. So this animation shows what is happening. So here you can see, now this is a landfill, and from that the leachate is produced, and then it is slowly coming, and then you can see this is the aquifer system or this soil system. So through that, how it is spreading. So here you can see the time versus concentration is plotted in this graph here. So now let us assume that here there is a municipal supply there. Say for example, so how it is reaching. So you can see that it is now after 600 days of this here the supply well is getting the contamination. So that is the way this movement takes place. So that is so very complicated process. So if it is not one important thing is that nothing is visible. So that is our major constraint. So we need to put so much of assumptions and then see what is happening. So that is why we have to be very careful, especially the engineers has to take lead, see that we shall not pollute even the soil or the we should not dump the waste like that without scientific landfilling, or we shall not put many kind of solvents like petroleum in tanks, which there is a possibility of leak. So that is what you can see that now finally contamination is reaching to the well, and that will create a lot of problems. And this is really realistically observed many parts of the country and many parts of the world also, so that you can see. So that is what is happening. And now you see that the system is so complicated. So as I mentioned, so the soil is concerned, all of you know that aquifer system, soil or for the porous media is concerned, it is so complicated system. So it depends upon things we do not know. So 1 feet to another feet, say 1 foot to another foot, or the 1 centimeter to another centimeter soil is so heterogeneous, so that we do not know what is realistically happening. Though for modeling sake, we put a number of assumption, number of simplification is put. You can see that what is happening here. Say if a contamination from this, how it is moving. Some places it will be fast moving, some places very slowly moving. So depending upon the soil heterogeneity, then anisotropy. So the system variations can take place as shown in this animation. So these are all the major kinds of issues. So here you can see, for example, this animation from one produced in US. So Columbia River is going. And now you see that if these are the pumping well, and then how much area it can affect when you are pumping water from a particular area. So you can see that these are the influence zone. It can be hundreds of meters influence zone is possible. So that way, if nearby areas are there, then it can also have this the contamination that can take place. So that is what we can observe in all these problems. So this 2-3 animation shows what are the major problems and how so complicated or how complex is the problem, that I hope all of you understood. Now coming to now let us see how we can protect and how we can control the pollution. So being engineers, we need to see that it is how we can do our, even your own well. So if you have got a well in your land, then how you can protect it. So once aquifer is contaminated, it is very difficult to restore. It is highly expensive. The last case studies which I will be presenting, you can see that how much expense and how many years we need to do the treatment. So it is always sensible to prevent pollution. So that is groundwater protection we always propagate. And the vulnerability of pollution depends on the aquifer nature, flow speed, and the unsaturated thickness. How much is unsaturated thickness? All this depends upon that. And we can so if your municipality or if your area, a lot of water is especially for municipal supply, if you are pumping groundwater, so then we need to see that we can prepare vulnerability map showing possibility of aquifer contamination, and then we can say that the areas we can protect. So there is a variety of models like American and European Union models are available. So they generally many places like Germany, they use so much groundwater. So there they protect the system with various zonation practices. So that I will show you. It is coming in the next slide. So now, if you have got a landfill or if you have got the pollutant is there, so then what are the source control strategies? So that is very important. So to minimize or prevent pollution before contamination, so we can see that various techniques are there, like volume waste we can reduce, and then most applicable in new sites like old sites abatement only we can look into. So this depends upon how much the volume can be reduced. So depends upon site situation, type of waste, etc. So advantage is that this reduce the correct accelerate time for stabilization of waste disposal. So that is what we can see. But many times it is difficult to increase the capital, lot of money to be spent, and then we need to monitor. And so here, if it is there, how much it is spreading, we need to see through the soil, and then how the spreading takes place. So that is also very important. So that way, some of the potential source control strategies. So in India, that much research is not taking place in the area. So there is a lot of scope for research. So one technique is, like as I mentioned, the volume reduction strategy. So we can reduce how much is the pollution, or how much is the waste. So there is all of you know, we can do recycling, like plastic recycling or many kind of recycling is possible. Then we can go for resource recovery, like a material recovery, waste to energy conversion. filtration, sand drying bed, etc. So there is a variety of methods for volume reduction strategies are there. And then comes physical or chemical alteration strategies. So this is especially being, since I am talking to mainly chemical engineers, so their chemical alteration strategy is very important. So we can chemically fix the contamination, so like neutralize, cementation, oxidation, reduction, biodegradation, etc. Then we can go for detoxification using thermal technologies, chemical, biological technologies, etc. And then degradation, so we can degrade the waste through various means, like by using chlorination, dechlorination, oxidation, etc. Then waste segregation, co-disposal, recharge, recirculation. So there is a variety of methods as far as physical and chemical alternation strategies concerned. So as I mentioned earlier, so there are European Union and American models are there. So for example, what this model says, so here we have got a pumping well. So that is a large quantity of water is pumping. So generally what they, in their system, what they do, there will be three types of zones they will be defining. So we have to protect the individual groundwater source like wells, boreholes, or springs. So here, through numerical simulation, we can identify which is a critical zone, like three zones. Zones 1 means 50 days of travel of water. So that is, this is so-called zone 1. And then 400 days means zone 2. And then zone 3, the entire catchment. So for example, if a well is there, that aquifer system, entire catchment. So there a variety of source protections. Say for example, if a particular groundwater well is there, especially for municipal supply, so they restrict all kinds of development in zone 1. So that is where 50 days of travel is there. And zone 2, restricted development only allowed. And zone 3, of course, some control like chemical industries or all those things are controlled. So that is the way we do the source protection zones as far as the groundwater protection is concerned. So now, since I'm talking to chemical engineers, so there is other kinds of technology, like once the like in a landfill or other areas, so we can this waste is concerned, we can isolate the waste material in a solid matrix before landfilling or stabilization or solidification. Then popular hazardous and radioactive waste disposal are there. So then we can chemically fix the waste in a solid matrix. So important stabilization solidification process include like a cement adding, additional lime or pozzolanic materials, embedding waste in thermoplastic materials, bitumen, paraffin, etc. So a variety of techniques are available as far as is concerned. So now, since I am a civil engineer, so we can also use certain well systems to protect our, especially the pump water from where we are pumping. So you see that this is a contaminant plume is identified. You can see here, and now. Let us assume that we have got a pumping well here. So then we can use, say, either another infiltration well or another kind of the way we are pumping. So that all those things can be controlled by variety of ways. So that is, we call it as plume management. So control movement of water phase and hence plume. So that is, I mean, the movement. So if we are pumping well here, so instead of going to this, we can make it such that it is slowly moving in other direction. And three common class of well system, like withdrawal through shallow system, deep system, injection of water, so like that. So this is but we need to have a number of observation wells for these kinds of problem. So this is the most assured system. More understanding of the system is required. So as I mentioned, our challenge is that we cannot see what is happening, and that is why it is so difficult. So here it is, moreover, but it is expensive also, since continuously pumping or recharging, all those things are required. So this is so-called, we can do the well system. So now let us assume that some area is already contaminated. So now first primary thing is that first thing is that we have to stop contamination. So if, say, for example, in your region, say petrol tank which is put in underground, that is, let us assume that is polluting the aquifer system. Then first thing is to be done is that we can identify that source and then stop that. So once groundwater pollute, how to restore. So that is what we are mainly discussing, to improve the acceptable standard. So that is the question we need to ask. So a few important steps are there. So first thing is that if you can identify the source, so that is one of the most important step, and then determine the distribution of pollution. So you see that how much area is polluted, where is the plume location, how the width and length of the plume. So all those things we need to look into. So then once the plume location is identified and its extent is identified, then we can go for remediation. So different kinds of remediation is possible. So here I would like to say that once an aquifer is polluted, groundwater is polluted, it is an impossible task to get to original level. But at least say, for example, if the TDS is concerned, if 3000 ppm is there, then if we can reduce at least 500 or 750 ppm, that is what we look into. So restoration to original level is impossible task. And first step is to containment of pollution. Then second step is remediation. So these remediations are concerned. On-site techniques are there, in-situ techniques are there. There are two kinds of remediation technique. One is on-site techniques, in-situ techniques. So on-site means generally we will be pumping out polluted water and then treat it, and then we can infiltrate down, or we can reuse it. That is so-called on-site technique. In-situ technique means we are not pumping out the water, but through bioremediation or like various kinds of techniques, we will be at the location itself, we will be remediating the polluted water. So that is in situ technique. So this is a table shows the difference between on-site technique and in situ technique. So here you can see generally used on-site technique is pump and treat. So you are pumping the wastewater or the polluted water and then treat it. And so then we can you say the soil is polluted, and we can excavate or dredge it, and then we can treat it, and then also we can go for solidification, stabilization, etc. So that is on-site technique. In situ techniques, so for example, if your land is polluted, so you have got a 10 cents of land, and then if the soil is or aquifer is polluted, then but if you are not using that water, then of course due to natural means, of course lot of bacterial activities and other kind of activities, naturally we can get attenuate, but it will take so many years, maybe say tens of years or 20, 30, 50, 100 or so years can take place. So that is, for example, now you all of you know that Bhopal tragedy. So that there the methyl isocyanate or some contamination is identified in that location, the groundwater. So still that water is not using, but now even after say 10, 20, 25 years, you can see that still the contamination is there. So that is what is identified. So natural attenuation is a very slow process. Then some of the other techniques like air sparging. So for example, if it is your contaminants, volatile organic contaminants like petroleum products, so we can go for air sparging. We can introduce air into the system. And then one most promising technique where all of us has to look is so-called bioremediation. So bioremediation means we are identifying the contamination, and then we identify certain bacteria, and then we allow that bacteria to grow in that area, and then that will be eating down this contamination. And then it mainly what is coming out to the carbon dioxide or say just plus water like that. So that is what is the most promising technique in a country like India. So then we can go for other kinds of treatment technique, like passive treatment wall, bioreactors, then carbon absorption, UV oxidation, slurry walls. A variety of techniques are available, and many of these techniques are used in developed countries like America, Canada, and UK or Germany, like countries. These are all very much used. So some of these important techniques will have a brief overview. So pump and treat, as I mentioned, it is if the plume is there. So what we do, we the contaminated water is taken out through pumping well, extraction wells, and there will be treatment building is there. They are treated, and then you can either put it back to a creek or you can directly utilize it. So that is called pump and treat, which is an on-site technique. And then in situ bioremediation, you can see here. So this is a bioremediation technique. So this area is polluted. So you identified the bacteria, and then you are allowing that bacteria to grow there by supplying oxygen and other nutrients, and then that will be automatically will be treatment will be taking place in the soil itself or the aquifer system itself. So the like as I mentioned, soil ventilation, air sparging, pump and treat, pump and waste, pump and use. So like that, these are some of the most important tools which we use for remediation. So as I mentioned, pump and treat is very much used, though in India we are not experimented this, but in Germany, Spain, and many countries, even while I was working in Germany, I have seen many plants where there are especially municipal areas where the pollution took place, and then they are going for pump and treat, and that is running, the plant is running for even so many years. So here, as you can see here, this is your contamination. So what we do, we can put a series of wells here, and then this plume is captured, and then contaminated water is pumped out. So contaminated groundwater is captured, pumped and treated, and you can re-infiltrate back if it is needed. For effective installation, accurately we have to determine the location of plume, determine the hydrological parameters of aquifer, etc. Pump and treat also contain plume movement. So the advantage is it is simple operation and design, but limitation is that so many years are required, long-term requirement, design failures, it is highly expensive, and not efficient for volatile organic contaminants. So this is what this animation shows what is happening in a pump and treat. So if it is homogeneous isotopic media, it is easy. So you can see that this is very fast, we can capture the contamination. But soil is very much heterogeneous. Reality is this figure. So this is what you can see, the reality. So then many times we will not be able to even capture all the contamination. So that is what is the issue especially with the pump and treat. So then bioremediation, as I mentioned, it is a very promising technology. So this is what you can see in a bioremediation. So here, if the contamination is flowing like this, so then we introduce nutrients and oxygen through wells, and then that will be, say here, the bacteria quality will be enhanced. So microbial process to degrade, transform contaminants to leave toxic or non-toxic forms, mitigating or eliminating contamination. The aerobic conditions is generally, if you put oxygen presence, means aerobic, and we can that will convert to carbon dioxide and water. And anaerobic conditions means nutrients such as sulfate, nitrate, etc. also can enhance the growth of the bacteria. And bioremediation mainly we do for organic compounds. So that is where you can see that the bacteria can destroy the organic compounds. So these important parameters like biodegradability, phase distribution, etc. Should be known for this. And then another technique which is used in some countries are called in situ flushing. So for example, if you identify a contaminant plume, since this is the movement of the plume is so slow, as you have seen, it can be many days or even many years. So what we do, we inject our aqueous solution to a zone of contaminated soil or groundwater down gradient, and a flushing solution like water surfactants, co-solvent, which is not polluting the groundwater. So in situ flushing enhances conventional pump and treat, and the success depends upon site specific. So we need to see various parameters, and efficiency depends upon solubility and mobility of the plume. So that is called in situ flushing. And then you can see air sparging. So as I mentioned, if it is volatile organic contaminants and there, we can inject oxygen or air in a high pressure, and that can convert, like detects protonal solvent. This it can convert into say by putting air, that will be the contamination will be converted. So here advantage, low maintenance, in situ remediation, etc. So these are the advantages of air sparging. So one important innovative technology developed in Germany is called groundwater circulation. Actually, I was also working in this area there while I was in Germany. So here, volatile organic contaminants are amenable to air stripping. So here, this is a well we introduce here. So there we put we supply air, and then groundwater. This is called a circulation zone will be generated, and then it will be air will be introduced. So it creates an artificial flow field, flushes, transform contamination and from aqueous phase to gaseous phase. And there's a single well or multiple wells can be there. Pumping in lower followed by air stripping, reinfiltration takes place, create a circulation zone. So this is so-called a circulation zone. You can see here. Pumping mechanisms control the circulation process, and then continuous flushing and dissolution, diffusion, all those things happens. So here, as you can see, it creates a complex 3D field. Efficiency depends upon radius of influence of the well. Advantage, less investment, and there is no need to pump out the groundwater, polluted water, but automatically takes place. It will be say within that zone, all the remediation will be taking place. But this limitation is that we need to exactly identify the location. And those who are interested, we can see some of the papers which was published by me while working in this area. So then coming to now another engineering aspect is, so as I mentioned, so this system is so complex, so we need to model it. So that is very important since we do not know what is happening realistically. So that is why groundwater modeling is so important. So here to make prediction about a groundwater system response to stress. So if we are pumping groundwater, then how the groundwater will be behaving, how the flow will be taking place. So to understand the system, we need to have a thinking tool. So that is so-called a model, groundwater model. The multidisciplinary approach is required. So groundwater flow and mass transport are important tools for. So we have a transport model, flow model, and transport model. So you can see that we can conceptualize the area like the boundary can be decided. Then governing equations like partial differential equation for flow and transport can be obtained. That is well developed in this area. And then we can solve those equation computation, and then finally we can get there, we can calibrate and validate also, and then we can run the model, and then we can get the various scenarios. So that is what is in the modeling process. So here physical phenomena, then we will be simplifying, and then a mathematical model will be developed, and then appropriate boundary conditions, initial condition, etc. will be applied, and then we can have a numerical algorithm and implementation using numerical techniques, various techniques like finite difference method, finite element method, finite volume, etc. Nowadays we use mesh-free method also. So variety of methods we can use it. So that is called a simulation. So now, as I mentioned, if you are going for a remediation, then pump and treat or a bioremediation, all those areas, we need to optimize also how much is to be pumped, how much, what kind of control is required. So optimization models also we can use it. So to find a maximum or minimum given objective function, like with the minimized cost maximum benefits. So it is what is will be always using. So for optimization, though there are so many classical methods nowadays, we are using artificial intelligence techniques like genetic algorithm, particle sum optimization, etc. So simulation, now you can connect the simulation model with optimization model. So we have got a very powerful tool. Since as an engineer, since I'm a number of PhD students are working in this area with me, and we have almost finished some 20 PhDs in this area. Here the simulation optimization model forecast water levels and effect on aquifer storage condition, and investigate optimal well spacing for withdrawing groundwater, then between proportional effluent reapply, and evaluate the rate of decline in groundwater table. So like that, various uses are there. So now that is especially simulation optimization model. So here these are the equations which we use for groundwater flow. This is for confined aquifer. This is for unconfined aquifer. So what we do, H indicates the head, P indicates the transmissivity in confined aquifer, K indicates the hydraulic conductivity. This is the pumping terms, QW, and the S is called storage coefficient or specific storage, the specific yield. So that is a time dependent equation. So you can see that this is nonlinear partial differential equation. So we need to solve this. By solving this equation, what we get the head variation throughout the aquifer system, and then using that head we can calculate the velocities within the system, and by Darcy's law. So this is the velocity with respect to xy direction, and then actual velocity can be calculated. And then that velocity, this velocity's value will be putting, this is called a transport equation, contaminant transport. So here you can see C is the concentration, it can be TDS or any kind of whatever you are putting. So R into del C by del T, R is called a retardation coefficient, and then dx dy are called the dispersion coefficient. And here these velocities we need to get Vx, Vy we need to get from the flow model, which we have seen in the last slide. So then if there is a pumping or other kind of things happens, so that is the term. So this is called a 2D transport equation. So nowadays, so many packages are available, like ModFlow for flow simulation, then contaminant simulation, MT3D, these are all finite difference based model. So you can use this free model, or you can buy available model FEM flow finite element method models that also you can buy and then use it. So that is about the flow and transport model. So now, say, as I mentioned, finite element method is very commonly used there. So you see that even we have written a book on finite element method. So here what we do, we replace the exact continuous solution by partial differential equation by algebraic system equation. So Galerkin formulation is used. So those who are interested, of course, our own lectures are available in the YouTube, and then you can look into that. So Galerkin formulation is commonly used. So we convert this partial differential equation to an algebraic system like this. So that is finally a conversion is done. So this is called an algebraic system, and then we apply the boundary condition, and then we can get the head variation or the concentration variation within the system. So this is for head flow, and this is for transport. So finally, an algebraic system is obtained, and that there will be putting the boundary condition to solve the flow and transport. So here, as I mentioned, those are industrial simulations. So recently we have developed a mesh-free method also. So there, finite element method is concerned, we need to have meshes, and that mesh development is difficult. So that is why mesh-free method is developed. So there, we simply use some shape functions, and those who are interested, some papers, we have published number of papers in this area. So you can see that this is mesh-free method. So we put only throw the nodes, the domain, and then we can use this for simulation purpose. So that is so-called mesh-free method. I will not go into the mathematics of this. Those who are interested, so papers, number of papers are listed here. Those papers you can download. Even if you search with my name, you can see these papers. So now finally, very similar to finite element method, mesh-free method also, we convert the flow and transport equation into algebraic system and solve it. So here then for optimization, we use the two techniques. One is called genetic algorithm, another one is called particle sum optimization. So genetic algorithm is a heuristic probabilistic method. So this is for optimization. Optimize the minimize the cost and maximize the benefits. So that way, genetic algorithm use a fitness function to measure the performance of trial function. Higher fitness values indicate closer proximity. So here, first we encode model parameters and generate initial population, then evaluate objective function, and then perform computation, and then a termination condition is applied. So that is the genetic algorithm. And another recently used technique is called particle sum optimization. So there, like birds are flying, or then how that pattern, based upon that pattern, we can create a swarm of particles. Then each particle position consists of m variables, where m is the number of unknowns in the optimization problem, and particle will reach search for this m-dimensional space, and then we can get an objective function measure to a quality of a solution. So here, this is so-called equation, which is say the velocity or the movement of the particle, and from that we can so these are all generated through a random numbers, and then using that this equation we can get it. So PSO is again a sample population generated, evaluate the objective function, each assumed solution is improved, and comparing its weakness, finally a termination condition is obtained. So as I mentioned, why I mentioned this thing. So this is a lot of mathematics there. You don't have to worry. We can develop a simulation model using finite element or mesh-free method, and we can develop a optimization model. Both can be combined together. So that is called simulation optimization model, and that can be effectively used for this groundwater, say like pump and treat or bioremediation. All this area we can use effectively. So this is a typical flow chart with the mesh-free method and the particle sum optimization. So before closing, I will just briefly go through two case studies. One is on optimal groundwater remediation by pump and treat using a finite element and elliptic genetic algorithm-based simulation optimization model. So here, purpose is to optimize the remediation of a large unconfined aquifer polluted with the total dissolved solids, and the simulation model is the finite element method, and the optimization is by genetic algorithm. So this anyway flow chart may not be interesting to you. So here, the objective function. So here we will be in pump and treat method. We have seen that we need to pump a lot of water. So that is one optimization, and another one is we need to treat that water. So that is the total cost should be minimum, and so that some of the constraints like our TDS, if it is 3,000, we want to reduce to 500 or 750, and the head variation should be under the control, and how much pumping should be taken place. So that is the optimization. So this model, one of my PhD students developed and applied for an aquifer system. This is in Gujarat, near Baroda or Vadodara. So Mahi River. So this is a Gujarat refinery. This area, a lot of pollution in 1970s and 80s took place, and then a plume was identified here. And this is a river, is Mahi River is flowing like this, and then there is a small drainage system is also there. So the aquifer system is various zones are shown here, and we used a finite element grid like this. And then you see that these are the plumes. So this is one major plume, another plume like that. These are the plume which you can see here. And here TDS concentration, it is about, you can see that it is about up to 2000, some hotspots. And then we need to, we use the simulation optimization model based on time tunnel method and genetic algorithm. And the TDS concentration, we want to reduce to 750 ppm. And that is what is, so this being a large area, so area is about 150 square kilometer area. So it our model showed that we need to put 36 years of combined rate of 15 remediation wells, and also some flushing also required, flushing ponds. So this is the flushing ponds location, like 4 ponds are supposed, so that the contamination from 2500 to we can reduce to around 750 ppm. So you see that here it is so expensive. The conversion is proposed to remediate the system. We need to put so much of water is to be pumped out like 1000 meter cube per day, and to get into a level of 750 ppm. And a combination of flushing and pumping is required. And you see that 36 years it may take. So you can see why it is so important to stop the pollution. And the cost is here about 66 crores rupees is required to remediate this aquifer system. So why I put it in front of you is that we need to be very, very careful, and then also we need to stop the pollution and how we can control the pollution. And then another case study is in Belgaum. This is the industries Hindalco. So here what they did is they have put some landfill with alumina industries there. So there they put it like this, and from here a plume was identified. And this is an aquifer system. So this is Markandeya River. And we did a simulation optimization model using mesh fit technique here. So here the area is about 72 square kilometer. And red mud, hydrols, silt, muddy, highly alkaline soil. This is from that the TDS as a pollution, and natural recharge is there, and then various aquifer related things are put here. So this is the plume which we identified. It is going up to around 2000 at the hotspot, and this is the plume which we have identified. This is actually some report by NGRI. So based upon that only we identified this plume. And now we used a simulation model, so-called measuring models. So we used this many nodes and then simulated it. So you can see that how the groundwater variation in this area. So here maximum and to minimum, water is flowing this direction. So this shows the groundwater direction. And then our aim was, so here, say after 20 years, since this is around 1995 or something, this contamination is identified. Then after 20 years, we simulated how much area is spread using the simulation model. And we compared with other available models, and then for flow and transport, we developed the model. And it was identified that we are getting very good match. And then we went for a simulation optimization model. So we used a particle sum optimization. So here, this is our concentration should be less than 750, and the head should not fall below 4 meter, and up to 1000 meter cube, 0 to 1000 meter cube per day is a pumping rate which is around. So here also we are proposing a pump and treat method. So this is the pumping cost, and this is the treatment cost. So that is a way this remediation design is done. And then you can see that the goal is to identify cost-effective remediation design, satisfying the constraints on TDS. So this paper was published in Environment Modeling System by my PhD students. So details you can download. So here cost versus number of iterations, and then you can see that pumping rate, say 4 wells we proposed, and the cost is around say 41.2 lakhs rupees. So that was the cost for remediation of this system. So here, once the remediation is done, through the mathematically, it was shown that 750 ppm, this is the, we can get using the simulation optimization model. We can identify where is the source. So this is actually 5 years of remediation is done for this particular area, which we did using mathematical and simulation optimization model. So finally, to conclude, so groundwater pollution is a major problem in many parts of many countries. So especially in India, we are not so much bothered, but now it is high time to look into this, since you see that earlier, say, we thought in 1970s, 80s, groundwater is a pure source of water. That is what we thought. But now, due to heavy industrialization, agriculture, farming, all those, the groundwater is polluted. So once an aquifer is polluted, restoration is very difficult. So we have seen various source of pollution, and then also our aim is to minimize the different forms of pollution. So if pollution occurs, if pollution is identified, then better thing is contain it. So we should not allow it to further to spread. And then, as I mentioned, if you are using this groundwater for drinking and other purposes, we need to go for protection zones. And then being engineers, especially civil or chemical or other environmental engineers, we need to go for innovative techniques. So bioremediation as a country, since we cannot spend so much of money, so we have seen 66 crores or 60 lakhs. That depends upon the plume size, what kind of contamination, how much area spreaded. So all these things are a big question mark. So bioremediation is a very promising technique. So that is lot of research work is needed. We need to identify the bacteria for each type of contamination and how we can enhance its activities, and then how we can do the remediation. So that is we need to see. And then like circulation belts, like in situ technique, that is also a promising technique. So groundwater management can be, as I mentioned, through mathematical model, simulation optimization model, we can do groundwater management. Simulation models are essential to study groundwater, since groundwater is very difficult to manage. So that way, simulation model like mesh-free methods or finite method, we can use it. Simulation optimization model very useful for remediation of the contaminated groundwater. And bioremediation is becoming more attractive because it is it's several advantages and minimal environmental impact. So finally, this is the last slide. So future direction, effective groundwater contamination control strategies, prevention is better than cure. So we need to look in that way. So remediation of contaminated site is essential. The development of effective in situ methods for groundwater pollution remediation, like effective bioremediation, that is one of the best methods. And then better remediation design we need to look into. So like we can use numerical simulations or artificial intelligence tools for these kinds of studies. So further finite element or mesh method or then like artificial intelligence techniques can be effectively utilized for groundwater remediation or designs. So that is about what I want to say today. So I have taken around 15 minutes. So now we can go for question and answer session. If you have got any questions, you can raise. So thank you very much, ACS, for giving me an opportunity to address the gathering. So thank you very much.